I'm going to show you how to use an interferometer, but first I want to show you a problem with the camera. The camera that I'm using has certain sensors that can detect different colours. Here is a white light source, and I'm going to place a diffraction grating in front of it so that we can see the emission spectrum from this white light source. And what can we see? Well, when I separate out the colours, we can see red, green, and blue almost as completely separate colours in the camera. When I view this with the naked eye, I don't see that. So the fact it looks not like a continuous spectrum, but like quite broad bands of individual colours, and I'm having to move the spectrum around so you can see it all, the grating around so you can see it all, that is a consequence of the detector, the sensor in my camera. It's not ideal. Let's have a look at some other sources of light, not white light sources. This Geissler tube contains hydrogen, and this is what it looks like with the diffraction grating. Well, I should say that's what it looks like through the camera with the diffraction grating. This is a helium-filled Geissler tube, and again, what it appears like through our diffraction grating. Here we're just looking at the first order to the right, the 0th order in the middle. Here is argon and the diffraction pattern for argon. The emission spectrum for argon. Well, this beautiful bright one is neon. And so bright, it might just be washing out. Yeah, there we go. If I drop the brightness down, you might just about see some emission lines from neon. The Geissler tubes are easy to drive. All you have to do is put a big potential difference across the gas, and the gas glows. And that's why I'm using this high tension power supply on the right. The display is broken. It doesn't tell you what the potential difference across it is anymore, but that doesn't matter. I'm just using a basic cardboard screen here. Well, helium looked the prettiest through our camera, so let's investigate the emission spectrum of helium using our interferometer. I'm going to place the helium Geissler tube here with a cardboard box with a hole in it, just to block off any light that's coming around that might make it difficult to see what's going on. There's our high tension power supply. Now the spectrometer has a slit here, and there's a screw that you can use to open and close the slit. If I turn this screw, the slit opens. If I turn it the other way, the slit will close. And I want the slit to be as narrow as I can, and vertical, and as narrow as I can reasonably get away with. The narrower it is, the more accurately I'll be able to determine the wavelengths of the light that is coming out of this helium when it's excited. We can focus with this and with this. So let me explain. This telescope, the objective telescope, is going to produce a collimated beam of light, which is going to be incident upon our diffraction grating, and our diffraction grating will produce a beautiful coloured spectrum. Okay. We will see the highest order we possibly can. Probably only the first order. This isn't very well maintained equipment and it's not wonderfully lined up. As you start deviating from the first order, it becomes harder and harder to see. By adjusting these two focusing knobs, you can produce a crisp, focused image of the slit. And by moving this eyepiece in and out, you can bring the crosshair, which is in this eyepiece, into focus. You might not be able to see it through here. You can't see it through there. There's a crosshair. And you'll be able to bring that into focus. In fact, I don't think the crosshair is actually on that eyepiece. The crosshair's somewhere else inside. Let's unscrew this and have a look. Yeah, so the crosshair is in there. You might put it on a piece of white paper. You might just be able to see it in there. So by adjusting the position of the eyepiece lens, we can bring the crosshair into focus as well. And that will provide a fiducial marker for us to line up the images of the different colours for the first and maybe the second and third order. Now, on this interferometer, there is a scale. This scale is a vernier scale, and it measures an angle. Doesn't really matter what angle, but it measures an angle. Right, I've clamped my phone in place, so it shouldn't be wiggling whilst I'm looking at this now. Maybe better light the scale. I've got a cylindrical lens here. Could use a spherical one, but I've got a cylindrical lens here. Just to magnify the scale a bit, so make it easier for me to see. But if I look really closely at this, right now, I mean, this isn't any particularly important number. That's 90, that's 85, 86, 87, more than 87.5 degrees. But how much more than 87.5 degrees? So you see the top part here is your vernier. The bottom part here, it's difficult to see because it's quite dirty. It needs to be maintained. That means taking all this top part off so I can clean it all. And that's not a small task. But anyway, you can read that that is 87.5, more than 87.5 degrees. Well, I can anyway. And how much more than 87.5 degrees? Well, that's where we line up the vernier. I make that 18 arc minutes, 18 arc minutes. So 18 arc minutes is 18 divided by 60 degrees, or 0.3 degrees. So this was 87.5 plus 0.3. I don't know why I'm typing that in the calculator. I can do that one in my head. That's 87.8 degrees. But as I rotate this stage around, you can see the angle is changing. And so you can then read off the position. Let's zoom out so you can see what I'm doing. Zoom out a bit more so you can see what I'm doing. As I rotate this around, like this, the scale here, the main scale, rotates around. And so you can measure the angle. So we're going to measure the angle of the 0th order. We're going to write that down. And then we're going to measure the angle of the first order for each of the colours. We're going to write them down as well. That's what we're going to do. From those angles, we'll be able to use the Fraunhofer diffraction equation, the Fraunhofer-Fresnel diffraction equation, the far-field Fraunhofer-Fresnel diffraction equation. Not enough alliteration. The far-field Fraunhofer-Fresnel diffraction formula. That's even more alliteration. We're going to use that to work out what those wavelengths are. So I'm going to write the equation. Someone's going to go onto YouTube comments and say, that's not the right equation. That's fine. You do you. N lambda equals D sine theta. Now, there's some information we know. We know that the diffraction grating we are using has 300 lines per millimeter. So the diffraction grating is 300 lines per millimeter. So if we want to know what D is, we take the reciprocal of that, and that gives us the millimeters per line. So D is equal to 1 over 300 millimeters per line. Well, what's that equal to? That's equal to 10 to the negative 3 over 300 meters per line. Probably don't need a calculator. Let's use one anyway. So 1e minus 3, I hate using this calculator, divided by 300. Oh, give me standard form. There we go. So we have 3.3. I'm not going to use a recurring dot. We don't do that in physics. 300 lines per millimeter was given to us to 3 significant figures, so let's stick with that. 3.33 times 10 to the negative 6 meters per line. That is what D is equal to in our equation. N, I don't know, we'll figure that out in a bit. I'm probably only going to be able to get N equals 1. So I'm going to record, I'm not going to bother recording which colour it is, it doesn't really matter. I'm just going to record a bunch of angles. So the first one I need is the 0th angle, the angle of the 0th order. And then I'm going to have a table with N and a bunch of different angles. Now these are the angles that are measured, so they need to be corrected. So let me put M. We're then going to calculate what the actual angle of each of those colours is. And then using the equation there, we're going to calculate what the wavelength that corresponds to is. In terms of angles, these are going to be measured in degrees. In terms of wavelengths, I'll probably stick this in nanometers. I could do the calculation myself, and I'll probably stick that in nanometers. So what we could then do is we could use E equals HF, same thing as E equals HC over lambda, to calculate what the excitation energy is for each of those wavelengths. Well, I'm not going to bother doing that. That's just doing numbers for the sake of numbers at the moment. But if you're investigating the energy levels and the transitions between energy levels, then that is what we would do. So let's get all this lined up and set up then. Here I've got a power supply, which is going to be powering just a simple ray box, which I'm going to use as a white light source to help me when I'm making my measurements. And I'm going to place my cylindrical lens next to it so I know where to find it. I'm not going to use my calculator for now. Pen, table, fine. Let's move over to the other side. On the other side, I've got my Geissler tube, which I turn on, producing that light that we see coming from our excited helium. I'm going to place this little box shield there and line this up. And in order to do that, I'm going to need a dark room. So I'm going to make the room dark. While I'm lining it up, I'm not going to bother with this telescope. I'm not even going to bother with the diffraction grating. I'll place that on the table so I know where to find it. I am just going to line up straight through here so I can see a single line. I can then put the diffraction grating in afterwards. So I'll turn the lights off. The room is now dark. Let's position this sensibly. Right-hand side, there's our helium, just as I said. There's our shield. Let's try and line this up. So I position the shield so that I can clearly see a line, a single line. I then position the slit, which is quite wide at the moment, so I can find the line like that. And now I can see quite clearly the line. Come on, I'll show you what it looks like. So from here, you can see quite clearly the line through that lens. Zoom in a bit. Through that lens. Let's get the light so you can see it all a bit more clearly. And that's what we're looking for. Now can you see it's right near the top of where the diffraction grating is going to be. It should be okay though. Let's get the diffraction grating. Let's place that in place. The diffraction grating's in place. If I look around at different angles, oh, there's some different colours there, but let's turn that light off, might make it a bit better. Let's go the other way. Oh no, I've lost it. Turn the light back on, can't see what I'm doing. Right, so the 0th order is there. Turn the light off, look to one side. There we've got blue, green, yellow, blah, 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 blah. Red. So I can line up with those colours with the telescope. Let's do that. Well, I'm going to make the slit narrower first, because I think a narrower slit will give me better results. But I don't want it so narrow that I can't see it. So that's probably as narrow as I want to make it. Now I need to adjust the two focusing knobs so that the image of the slit is going to be, oops, in focus. So right now I'm looking through the telescope and I can see the image of the slit, but it's a bit blurry. So you'd have to have long arms for this. I'm going to lean along, and it's a little bit of trial and error. There we go. That is now in focus, and I'm going to adjust the position of my eyepiece to get the crosshair in focus. And now I need to adjust the focus again of the slit. As I say, a little bit of trial and error, and eventually you get it all lined up. So that's pretty good. I'll show you what it looks like. So right now this is still the 0th order and I haven't measured the angle yet. But I'll place the lights here so you can see a bit of glare, because that helps you see all of the crosshair. And so if I move this closer, camera's telling me move back to improve focus. No, I don't want to. Okay, get a bit more glare. Might be able to see a bit better. So I'm not sure if you can see the crosshair. I'm not sure if you can see the line, but they're all in focus to me. I just can't get the camera to behave itself because, you know, I'm just holding it against the eyepiece. So that's never going to work very well. Right, I think that's as good as you're going to see it. Crosshair, and you can rotate the crosshair around if you want to. But I'm going to leave it like that. That's pretty much in focus. Now we're going to line it up like that, and then we're going to measure that angle, the 0th order angle. I'm going to turn the big light on to help me. You've already seen the scale, so you know you don't need to see that again. But I'm just going to do this because it's going to help me see what I'm doing. You're going to have to see my back as I read it, which I'll tuck my shirt in first. Right, so here we are. This is the vernier I'm reading from. Hopefully you can see this okay. Careful not to knock any of the telescopes or any of the optics. More than 80. A little bit more than 85. Right, it's 85.0 and 4 arc minutes. So I could write down 85.0 degrees and 4 minutes using the usual notation. And I could turn that into an angle with my calculator, all in degrees, 85 plus 4 divided by 60, 85.06. I'm going to call that 85.1. 85.06 is close enough. 85.1 degrees. And so that's the angle that I must subtract from every one of my measurements. Now let's find the first order. So let's turn the lights off. Because it's quite dark, I'll put that backlight on just so you can see a bit of a silhouette of what I'm doing. Usually I'd have it in total darkness. Right, let's go find that first order. So I'm going to move the telescope around until I see, aha, there they are, a whole bunch of lines. Come on, I'll show you what it looks like. Whole bunch of lines. So this is my first order. Let me just look through the eyepiece. Come on, line it up. That might be about as good as I'm going to get. You can see there's a whole bunch of lines. Blue lines, green lines. That's fine. And I can keep moving this around. And there's an orange line. There's a red line. If I move this back, red, orange, greeny, blue. So let's go pick a colour. Let's pick that blue one. I'm going to line the blue one up with the crosshair. Very carefully. And there are little screws you can use to make fine position adjustments. You don't have to just grab the arm and pull it around. There's too much glare from out here, so I'm going to turn that off for a second. I think that's lined up. So now we're going to measure the angle, first order for that blue. Okay, so first order I've got 92.5 degrees and 15 arc minutes. So 92.5 plus 15 divided by 60. Probably don't need to use a calculator for that, but again, I will. 92.75, I'm going to call it 92.8. 92.8 degrees. And that's blue. I will record the colour actually, because that'll be interesting. Right, let's go find another one. Turn the lights off. We're going to look for green now. Whoops. There's quite a few green lines, but there's a particularly bright green line. Just, oh, I think that might have messed up my lamp. There's a particularly bright green line right there. So let's go with the bright one. I could measure every single one, of course, and if I'm doing this properly, I would. But I'm not. I'm just going to measure the brightest ones for now, because I'm only demonstrating how to use the equipment. So I've turned the light on. This is green. It's part of the first order still. Let's read this angle. 91, 2, 3, 93.5, and so 13 arc minutes. 93.5, double check that. 93.5 and 13 arc minutes. So 93.5 and 93.5 plus 13 divided by 60. 93.71, let's call it 7. So let's say 93.7. So that's two of them. Now I'm going to do the rest without recording it. And I'm going to show you the tape. Excuse me. I'm going to do the rest without recording it. Then I'm going to show you the table and what we do with it next. So I've now got blue, green, yellow and red. I'm now going to go and see if I can see the second order. Not sure if I'll manage it, but let's see what I can see. Trying to find the second order with this badly maintained interferometer. So that was red. Let's move around. Oh, there's blue. and there's the green. I can see them, but I know it's going to be too pale for the camera to pick up. So there's the blue. See if I got it crosshair perfectly lined up with it. Oh, I can't see very well. I think that's the blue. So I nearly got all of the second order, but I couldn't see the second order red. It wasn't bright enough. Then the third order, I couldn't see blue, green, but I could see the third order yellow as well. So I might as well record that at the same time. 110, 115, 16, 17, 16.5, and 9. 116.5 and 9 arc minutes. 116.7. And so there we are. That's about as good as I'm going to do. Let's turn everything off and analyse the results. Don't need that on anymore. Certainly don't need this on anymore. Let's position the camera in a sensible place. So here's my table of results. You can see we've got all the colours that I was able to see and the order of them. I couldn't see any more, it just wasn't bright enough, but there were a few greeny lines that I haven't recorded because, again, I'm just trying to do this quite quickly. But there were quite a few green lines in the first order I haven't recorded, and I could perhaps just about make them out in the second order as well, but certainly not the third order. So now I have to subtract 85.1 from every single one of these. And with the power of the pause button, boosh, there they are. Now, what I've just done here would fail competency 4 in the A-level practical endorsement. Can you tell why? I will tell you at the end, but drop a message in the comments if you can tell why in advance, and then drop a message in the comments if you agree or you disagree, or if you spotted it, or just comment. Right, okay, let's do these calculations then. We're now going to calculate lambda for each one of these using D, which is this. This is much easier with reverse Polish notation, but I'm stuck using this horrible calculator because I haven't brought my nice calculator with me. So this could take a while. Let's do this. Ugh, that was awful. Right, there we go. There are the wavelengths. And what do you see? 446.2 and then 442.2. So 4 nanometers different between these two. It's not terrible. That's about, well, it's less than 1% difference between these two, which is quite good for this apparatus. Green, what have we got? 498, 497.9. I mean, that's incredible agreement on that green. Yellow, 589.7, 585.8, 581.6. So a difference there of, what's that, about 8 under 5. So a little bit more than 1%, less than 2% uncertainty. Still not bad. And then, of course, we've got only one measurement of red. And then the wavelengths look sensible. They look like they're in the right sort of ballpark. Now, as I said, the next step would be to take these wavelengths, plug them into here to get a bunch of excitation energies. Bear in mind that these yellows, you would have to combine these wavelengths. Oh, not that one, that one. You'd have to combine these wavelengths for the yellows because they're all the same. They're all the same color, so you calculate a mean of them. The blue here and the blue there, you'd calculate a mean of those two. The red one, oh, where's the green? We've only got one green. Oh, we've got two greens. There we go. We've got a green there and we've got a green there. So you'd have to calculate a mean of those two. And then, well, we've only got one red. So we don't have a choice. That's the red we use. But that also gives us some uncertainties. I mean, yes, we've got uncertainties related to the resolution of the instrument. But then because we've got repeat measurements, we've also got uncertainties we can calculate from that. Now, in a darker room, with a brighter lamp, or a brighter Geissler tube, we could get, and better aligned equipment, of course, we could get even more high resolution, or not resolution, even more accurate, let's say, angles, and therefore even less uncertainty on these on these wavelengths. But that's not bad. Right, did you spot the 𝗟𝗶_4 mistake that I'm going to pretend I made deliberately? The unit is listed up here, and then I've written the unit after each of these angles, after each of these. So that would be a fail. You should only have the unit up here, not after each number. What a silly thing to do. And of course that opens up a whole can of worms. Is degree a unit? And I'll let the mathematicians who enjoy commenting on my videos comment on whether they think a degree is a unit or not. You have at it, you enjoy yourselves. But there we are. That is how to use a interferometer. Sorry, not an interferometer, stupid. A spectrometer to determine wavelengths. Tremendously useful.